In this video, we're going to talk about how percentage yield is affected by one or more reactants being in short supply. In other words, when there is a limiting reactant. So for this, we're going to look at the reaction of copper oxide and carbon powder to give pure copper and carbon dioxide. Now, before we do anything else, we have to make sure we balance this chemical equation and write state symbols, and we do that by putting a 2 in front of the copper oxide so that the oxygens are balanced, and a corresponding 2 there to balance the coppers on the other side. Now, the other thing to factor in is your state symbols. So copper oxide needs to be a solid, carbon is a solid, copper will also be a solid, and carbon dioxide will be a gas. So let's say in this experiment we're starting with roughly about 2.60 grams of the copper oxide, and we mix it with, let's say, roughly about 0.22 grams of copper. Now, because there's two reactants, what is going to happen is that when these two reactants come together, one of them is going to run out before the other. And the reason this is important is because it will affect how much of the product we produce. If we calculate yield based on one reactant without knowing if it's the limiting or not, we will already have a yield value that's misrepresentative. So we do have to first work out which one is the limiting reactant. To do so, we're going to base ourselves around one of the reactants. In this case, let's use the copper oxide. So how do we calculate which one's limiting based on this? We start by converting the grams into moles, using the formula number of moles equals mass over molar mass. Now, the molar mass of copper oxide, depending on the periodic table you use, will be slightly different, but I am getting a value of 79.545, and the mass in this case is 2.6 from the question itself. This gives us a value of roughly 0.03 269. Okay, now the next thing we do based on this is we work out, based on this amount of moles, how much carbon we would actually need. In other words, how much carbon would we need to completely react with the copper oxide? And to do this, we apply the molar ratio. The molar ratio is given to us in the question. I'm going to darken it here. So the molar ratio between copper oxide and the carbon is a 2:1 ratio. So what we're going to do is take the number of moles we just worked out and apply the molar ratio. The way we apply molar ratios are as follows. So we find the moles of carbon is 0.03269 divided by the molar ratio of the thing we're starting with, which is 2, times by the thing we're going to, which in this case is the 1. So what does that give us? This gives us 0.0163. Okay, now what we need to do is compare the moles of carbon we need, which is what this is, to the moles of carbon we actually have. And to do this, we need to go back to the question. I'm just going to draw a little bit of a line here. Okay, how much carbon do we actually have? We start with the mass that we've added in, and we convert that to moles as well. So we go number of moles equals mass over molar mass. So now, in this case, the molar mass of carbon is 12.01. 12.01, and the mass we're starting with is 0.22. So when we plug that into our calculators, here we get a value of 0.0183. In other words, we have more carbon than we need. We just worked out that we needed 0.0163 moles of carbon to completely react with the copper oxide, but we actually have 0.0183. So, in other words, what we're going to say is we're going to call the carbon the excess reactant. It's in excess. We have more than what we need. So in other words, the limiting reactant in this case is the copper oxide. So we're going to write limiting on the top there. Okay, so what do we do next? The next thing we do is we work out how much of our product is produced based on the moles of the limiting reactant. So the moles of the limiting here are the copper oxide, which is 0.03269. Now what we're going to do is apply a ratio to convert from the moles of copper oxide to the moles of copper. And to do that, we take our 0.03269, we divide by the ratio number of the thing we're starting with, in this case the copper oxide, so divide by 2, and then we times by the thing we're going to, which is copper, the ratio number of copper, which is 2. And so if you divide by 2 and times by 2, you're just getting 0.03269 again. All right, the next thing we need to do is compare the moles of copper we expect. So this is the moles of copper we've just worked out, expected, to how much is actually produced. Or, alternatively, compare the mass of copper that is expected to how much is actually produced. Mass is easy to deal with because we can weigh it and work that out. So what we're going to do now is we're going to convert the moles of copper to mass by using the number of moles equals mass over molar mass formula. But here the formula is rearranged to say mass equals number of moles times molar mass. So the number of moles is 0.03269 and the molar mass of copper is 63.55. And this gives us roughly 2.077 grams. Now, we're not done yet. This is how much copper we're expecting to produce in grams. Now we've got to compare that to how much we actually produce. So here we've got the theoretical, expected or the theoretical yield. And let's say we weighed the copper and worked out the actual yield is something like 2.01 grams. Now, you have to be careful when you're weighing the copper because there might be some unreacted reactant. Whichever one is not the limiting reactant might still be there. You might also have some unreacted reactant of the other reactant if they don't completely react. So you've just got to be aware of what you're weighing and if there's any inaccuracies. But let's say we've worked out what the actual yield is and we've got about 2.01 grams there. Now, the formula for percentage yield is actual over theoretical times 100. So in this case, we've got the actual, which is 2.01. We've got the theoretical, which is 2.077. We do that times 100, and that gives us roughly 96.8%, rounded to 3 significant figures because that's how many sig figs were in the values we used. So that is our percentage yield. Now that's quite a high percentage yield. If a percentage yield is accurately that, it's actually really good, but you've got to keep in mind there might be some errors or inaccuracies that might lead to that being overestimated. But in this case, with the values we've got, that's the value we've calculated.